Okay, the next section is about knowledge distillation. Knowledge distillation. What is the meaning by knowledge distillation? In the knowledge distillation, we are going to learn a source model and distill its knowledge to a target model. This can lead to a better model with small architecture or faster training. So usually in the literatures, they call it source or teacher model. And we want to transfer the knowledge from the teacher to student model, or we have the target or student model. Okay. Given a teacher network on the domain D, enhance the training of usually a smaller student network on the same domain D using knowledge of a teacher network. So we have the network from the source, this is the teacher, and we have the network from the student, and at the end we are going to match between the output from the teacher and the output from the student. So we are going done by matching the output of the source and the target model, and we would like to calculate a new loss term. New loss term means we are going to use some loss function. We can use MSE loss, MSE. It is mean square error, or we can use the KL divergence. KL divergence I will explain a little bit later. And this usually used to for making the source and the target output similar in addition to the original loss term. So the original loss term is the cross entropy loss. So if the loss is small, yeah, we can say that the model between the teacher and the student, they are similar. In the knowledge distillation, they will use one new parameter, they call it temperature. Maybe I will not explain in detail about the temperature, but there is a new parameter. Maybe if you learn in the deep learning, there is a parameter about learning rate. Okay. And also there's another parameter about dropout rate and etc. Okay. It is also the same. In the knowledge distillation, they have the temperature. So the temperature, we can use the temperature to make a softer probability distribution over classes. So we know about the softmax function. Okay. In the softmax function, usually we just use the E. And with the loss function, we usually use the exp. Okay. But we can also apply with the temperature, T. So T means the temperature. And in this formula, we have the ZQ. Z is the logit, okay, and Q is the probability. Q is the probability and Z is the logit. And we can have the loss function, or we use the soft target as the agitational labels to train the student model, and we will have this kind of function. You don't need to be afraid with this formula. It is only to look at which one is better for this loss function or this loss function. CE. CE means the cross entropy. Okay. Cross entropy function. So this is loss between Y and Q. What is Y? Y is the ground truth labels, and Q is the target model outputs. So we want to calculate the loss, the cross entropy of the ground truth and the target model. And we want to also calculate the cross entropy between the P and Q. P is the source model output and Q is the target model output. Okay, so we will check which one is higher. So we can just make the probability with the alpha. Okay, so the alpha means something about the weight. So we want to know which one is more important, whether the loss between the actual and the target or the loss between the source and the target. Yeah. So we can use also with the temperature. Okay. So the temperature can be used only for this target and source, or sometimes we can also combine with the other loss function. So we can use the Kolberg-Leibler divergence, or we call it the KL divergence. It is to calculate the distance between two distribution. We call it the P and Q. So this is the KL divergence of distribution P and the distribution Q. So we have the sigma of Px log by Px divided by Qx. So let's say I just have a, let me just have a very simple number. Let's x to be 1, 2. Okay. And the teacher model output with softened probability with temperature T equals to 2. I can show you like this one. So this is the probability from the teacher. So we have 3, 0 0.7, 0 0.2, and 0 0.1. And this is the output from the student model, 0 0.6, 0 0.3, 0 0.1. Okay. And let's assume that the uh, ground truth, the ground truth label, like this one, 1, 0, 0. So it means this is the label, the class number 1 is 1, the value number 2 is 0, the value number 3 is 0. So the actual data has been labeled with the value number 1. So the X is the data that we have, and this is the Y. We know we have the X, it is the features, okay? And we want to classify into Y. Y is the class. Using the data here, we want, you know that the class is 1, 0, 0. Now, at first, you need to compute the teacher predictions with the temperature T. It means now we can do the softmax probabilities from the teacher model that are computed with the temperature T using the formula that I explained before. We use the EXP, ZI divided by T divided by the sigma of AXP, ZJ divided by T. So if we have the teacher 0 0.7, 0 0.2, 0 0.1, assume they are already softened by T equals to 2. Okay. Yeah, so we have this value, so we can just calculate. Okay. We have the student loss. Okay. The student loss means the we use the distillation and the ground truth. Okay. The total loss is a combination of distillation loss, student mimic teacher, and the ground truth loss. So students align with the true labels. So if we have the teacher, okay, so we can create the student. So we can calculate the loss between the teacher and the student, and then we can also calculate with the ground truth. Okay. So in the ground truth, we can also get the loss. So we want to know the loss of this, the loss between the ground truth and student, and we also want to know the loss between the teacher and student. And at the end, we want to create the total loss. The total loss means this loss plus this loss. And let's assume that we have the alpha is the width, and make it the width as equal. So this one have the width 0.5, and this one also have the width 0.5. So the distillation loss, we can measure the KL divergence between the teacher and the student. So the loss distillation between the teacher and the student, we can use this KL divergence. So we include the T power of 2, okay, and we do the sigma of the P teacher multiplied by the log P teacher divided by the P student. Yes. Let's say this one. So we have the T, which is the temperature, and then the P teacher multiplied by log P teacher divided by P students. Given the value, which is P teacher is 0.7, 0.2, 0.1, and the P student is 0.6, 0.3, and 0.1 with the T equals to 2. So we can just embed the loss distillation between the teacher and the student. So 2 power of 2. And then we do the summation of 0.7 multiplied by log 0.7. This is from the teacher, and 0.6 it is from the student. And then we calculate with 0.2. This is from the teacher, and the value from the teacher divided by the value from the student, plus 0.1 multiplied by log 0.1 from the teacher, but divided by the value from the student. Then you can do like this one. So what I mentioned before, moment. So you can use the calculator, the same like before. Okay, and the formula you can see it is log. In the formula you can see that it is using the log function, but in the major function, in the major loss function, it used the natural logarithm. Okay, so if it is log here, log 1.1667. Okay, so 0.6, 0.7 divided by 0.6. So we have the value 0.7 divided by 0.6, and the value is 1.1667. So let me just round to the nearest value, which is 1.1667. We have 1.1667, and then we use the natural logarithm. So the value is 0.1541, 154. Okay, this one is 154. And then the other is log 0.6667. So I also adopt the natural logarithm. The natural logarithm is 0.6667 with the ln. Okay. So we have the value 0.405 with negative value. And the log is logarithm 1, so it means 0. Okay. So if it is 1 with ln, ln logarithm, natural logarithm of 1 is 0. Then at the end, we can get the loss function, give you the loss as much as minus 0.1072. This is the loss between the teacher and student. Okay. And next, we want to calculate the loss between the student and the, we want to check the loss between the ground truth and the student. Okay. So the ground truth is the actual values, and we want to get the output from the student and then calculate the loss. So we can use the standard cross entropy, which is this one. So you already know the standard cross entropy from the previous example. So the loss will be 1, this is the actual, multiplied by log 0.6, log 0.6, 0, log 0.3, and 0, log 0.1. Because 0 multiplied by any value will be 0, 0 multiplied by any value will be 0, so the remaining will be log 0.6. And we have the negative, so we have the value as the minus and minus. So this is the loss from the loss between the y, the actual value or the ground truth value, and the student network. And at the end, we need to calculate the total loss. Okay, so the total loss means the loss from the distillation. So the loss in the distillation, it is the loss between the teacher and the student. And the loss, this one, is the loss between the ground truth and the student. Okay. Yeah. If you look at the formula, some variation, you can include the t. So you can include t power of 2. Okay. Yeah, that's the variation. But let me just use the very simple total loss. So we apply the alpha, it is the width. And let's assume the alpha is 0.5. So the width is equal between the loss of distillation and the loss of the ground truth and the student. Then we have the 0.5 multiplied by 0.1072 plus 0.5 multiplied by 0.511. Then the total loss is 0.3091. Okay. So is it good? We don't know. So after we have this loss, you need to again update the weight. Yeah. If you can update the weight, you can get the new student network and then check again the loss. The goal is to get the minimum loss. If the total loss is minimum, then you can use that model for your application. The next step is you can do the back propagation and do the weight update. The weight update means you can update the teacher network update and then the student network update. So in this case, I just give you a simple example. So the weight is already given. The gradient for the student model are derived from the total loss. So using the combination of gradient from the distillation loss and the gradient from the ground truth loss. So we have the loss distill. It is from the teacher and student network. And then we have the loss through, which is the loss between the ground truth and the student network. After we do the updating with, and then we do the back propagation, we can again update the total loss. So we want to get the total loss with, which is the minimum. Okay, the next section is about the parameter efficient fine tuning, PEFT. So what is PEFT? What you learned before, it was related to the foul fine tuning. Full fine tuning. So in the full fine-tuning is literally a method of updating all parameters of a model. So we have the parameters from the existing model, let's say using the BERT. So we use the all parameters and then we transfer into a new data set, or yeah, we can say we transfer into a student network. So these techniques adjust all weights of the model to improve the performance of specific tests. Since it adjusts the entire model, it requires a lot of memory and computational resources. So in the full fine-tuning, yeah, they use every of the model. So you use all the weights, and it is very high computational resources. That's why there is a method. There are two additional methods. We call it LoRa and QLoRa, which address how to reduce the computational resources. And we want to use that one. Even though the computational resources reduce, the performance is still almost the same with the full fine-tuning. So they call it, it is the parameter efficient fine-tuning. So we don't need to use all the parameters, we just use the important parameters. The parameter efficient fine-tuning is a method for fine-tuning a model by updating only a specific set of parameters rather than adjusting all of the model parameters. So we don't need to calculate all models, but we just calculate the specific parameters only. This provides effective performance improvement while reducing computational resource and memory usage. So in the PEFT, they call it freeze. Freeze means, yeah, it will some model, it will not be changed, because if you know, with the back propagation, in the back propagation, yeah, you will change the weight will be updated according to the loss. But when you freeze this one, when you freeze, so it means uh, only selected parts of the weight will be adjusted. Yeah. So not all the weights will be updated, but only some selected parts. Yeah. So using the approaches like LoRa, low rank adaptation, and QLoRa, quantized LoRa, so we can do this parameter efficient fine-tuning. So LoRa, what is the meaning by LoRa? LoRa, or low rank adaptation, is a form of PEFT, parameter efficient fine-tuning, that use low rank matrices to adjust parameters in the specific layers of the model. So LoRa enables efficient tuning by adjusting only some parameters without updating the entire model. So you don't need to update. So if you have a very big model like BERT, you can see now GPT has 17 billion something parameters. So if you do with all the parameters, of course, it requires a lot of resources. So they just select some parameters and they will create another weight, or they create another model. The idea of the LoRa is to create A and B. Okay, so what is A, what is B? So LoRa, or low rank adaptation, the purpose is efficient fine-tuning for large models. So if you have a very huge model, so we can use LoRa. How it works, instead of updating all the parameters, it inserts low rank matrices A and B into weight matrices. So the full fine-tuning, you put the X and then you will multiply with the weight, and then you will get a new matrix. And this weight will be for all the parameters. But in the LoRa, okay, you have X and then you will Also, this is the W. So the W, yeah, it is the smaller or only the selected one, and we want to select based on the A and B. Okay. So A and B is two additional matrix that can represent the smaller values from the existing W. And then, yeah, when we can extract this one, so we can calculate this and we will add this one. So we will have a new updated weights. The advantages is to reduce the memory usage and computing costs and keep base model parameters frozen. Sometimes in the base model, yeah, you have some important parameters and those parameters will be frozen or they will not be changed. So LoRa reduce updates by focusing on the rank. The goal is fine-tuning a pre-trained model weight matrix W for a linear transformation. So let's say I have a pre-trained weight matrix W. So this is from the pre-trained model. Let's say I use the pre-trained model, let's say BERT. Okay. Yeah, this is the weight from the pre-trained model. And then I want to do the learn adaptation. Yeah. So the learn adaptation means I want to get the sigma W, sorry, the delta W. Okay, the delta W means the short version of the W by looking at the A and B. So what is A and B? Okay. A and B, it is a matrix, okay, and it is a matrix of size D multiplied by R. Okay. D is the size of the model original weight matrix, and R is the low rank. So if you learn about the linear algebra, we can have a rank. Okay. Rank, it means we want to have a smaller representation from the original matrix. So D is the size of the original weight, and R is the lower rank, and usually it is a small value, whether it is 1 or 2. And it represents the direction of the changes. P, on the other hand, it is the matrix of size R multiplied by D. It will like to scale the change direction defined by A. So we have the D multiplied by R for the A, and then we have B, which is R multiplied by D. So we want to find what is the best representation in the rank to make the weight more representative by just finding the delta W. Okay. These metrics are trainable parameters during fine-tuning, but they are much smaller than the original weight matrix W. So we can reduce the memory and the compute overhead. So let's say I'm just using the R equals to 1. Okay. So R equals to 1 means, yeah, R, yeah, this one, R is 1. So you can make R is 1 or R is 2. Sometimes you can make 3, 4, but the smaller is the better. So let's make R equals to 1. So when R equals to 1, then let's say the A is initialized randomly. Yeah. D multiplied by R. So let's say I have the matrix previously. There it is 2 multiplied by 2. Okay. Then I can have the A is 0.2. This is 2 multiplied by 1 matrix. Okay, the A is 2 multiplied by 1, and then we have B is 1 multiplied by 2. Okay, 1 row multiplied by 2 columns. Okay. then yeah, we can just do the matrix multiplication to get the delta width and compute the delta width. The low rank update delta W is computed as like this one. 0.2 multiplied by 0.5, 0.2 multiplied by 0.3 minus 0.1 multiplied by 0.5 and 0.1 minus multiplied by 0.3. Then we can get the delta W as this one. Okay. After we have this delta W, then we would like to update the W. Updating the W means it means we are going to fine tune the width matrix. Okay. We fine tune the width matrix using the low rank. So the new W will be the existing W plus the delta W. So the W is this one plus the delta W. It is given from the A multiplied by B. So we just simply add those two metrics and then yeah, we get the value. The new W is 1.1, 0.44, 0.35, and 0.83. The updated W, which has been fine-tuned, will be used as a model on the target dataset. Okay. So of course, yeah, this kind of mechanism, I just show you with a very simple example, but in the network itself, so there will be a back propagation. So they will update again this W according to the loss function. Okay, so I just show you how to do the calculation for this LoRa, and you can see that if the matrix is having like 17 billion parameter, okay, if we have the 17 billion parameters, maybe there will be 17 billion columns multiply, not 17 billion columns, maybe 100 million multiply by something 1,000 or something. So if it is very huge, so you cannot do the calculation well. So we can make the A and B with the low rank, and then we can calculate. Then that one of the LoRa approach will give you a better result. So the other kind of methods, we call it QLoRa. Okay. The QLoRa is the quantized low rank adaptation. The QLoRa is an extension of the LoRa techniques that quantize model parameters to tune them more efficiently. In the LoRa, they don't apply the quantization. So in the LoRa, they use the model 16-bit. So in the QLoRa, they try to adopt a lower bit. So quantization is a technique that allows model parameters to be expressed in the low precision, saving memory and computational resources. So the quantized LoRa, the purpose is to combine LoRa with quantization for even more efficiency. And then the quantization means that they will convert the weights to 4-bit precision to save more memory. What does it mean by 4-bit precision? Okay, we will look at the example later. So LoRa applies low-rank adapters on top of quantized weights for fine-tuning. So we have the adapters, but the adapters is low rank. Okay, so if I mentioned to you before, the rank, okay, in the linear algebra means the representation of the matrix with the smaller dimension. The advantage is it enables fine-tuning on GPU with limited memory. So if you have a GPU, but the GPU has very limited memory, then the fine-tuning will be good. And it maintains model performance despite quantization. So the model performance will be still almost the same or similar. So if the quantization, we want to get the quantization, it is to reduce the precision width of the safe memory, and usually it maps float values to integer. What does it mean? We have the quantized width. We want to round up the W into a scale value. Scale value, it is to map this width into integers. So float, do you know float? Float is like numbers with decimal 0.3, 0.5, okay, or 0.11 something. And we want to change this value into specific integers. And because they call it as 4 bits. Okay. Do you know 4 bits? 4 bits, usually when we do with the computer memory, we use the binary number 0, 0, 0, 0, like this one. So if it is 4 placement, then we call this is 4 bits because we have 0, 0, 0, 1. There are 4 0, 1, 0, okay, or 0, 0, 1, 0, 1. So there's a possibility like 0, 0, 1, 1, okay, and so on. So 4 bits, we want to limit the data into only these 4 bits. If it is 16 bits, of course, there will be 16 numbers. Okay. Then you can see that if we have only 4 bits, then the data is reduced. Okay. So the idea of this quantization, they want to reduce into 4 bits. And when we do the quantize, so we want to round the weight, and after we have rounded value, we will again dequantize. Dequantize means we will rescale again with the S value. So let's suppose S equals to 0.1. Okay. If S equals to 0.1, and let's say I have the weight value, so I use the same weight value from the previous one. So the quantized weight, means the weight that we have, which is 0, 1.0, 0.5, 0.3, 0.8, divided by S. S is 0.1. Then we can get the value like this one. So the float value now becomes integer. The float value becomes integer. 1.0 divided by 0.1 now becomes 10. 0.5 divided by 0.1, it becomes 5. 0.3 divided by 0.1, it becomes 3. And this one becomes 8. Okay. So this scale is just to show you very simple one. Okay. And when we do the dequantize, we have the WQ, okay, and then we want to scale up again. The scale is using the S equals to 0.1. Then the value from WQ, which is this one, it will be written back to the original value. Okay. So the updated the W dequantize, this one, which has been fine-tuned, will be used as a model on the target dataset. But maybe you will have questions. Professor, so the value is the same. Why? Yeah, now, because it is the very small example, so we can get the same value. But when you have a very big matrix, if you have a big matrices, then yeah, the value will not be the same like this one. So the dequantized width or W dequantized matches the original W because we quantize and dequantize without adding updates yet. Yeah. So the W and the W dequantize, they are the same. Why? Because there is still no update about the W. In the real application, so rounding during the quantization often introduce small errors. So our value is very good, like 0.5 and 0.3. Okay, so this is very good. But when the value is very, very small, let's say 0.3145, something like this one, then there will be some small errors. And if it is very small, it will accumulate in larger or more complex examples. So this simplification ensures hand calculations are manageable. So yeah, because I show you with the very simple numbers, of course they are the same. But in the real application, yeah, they are totally can be different. So in the Hugging Face, yeah, it is one of the popular tools for the NLP. You can take a look. There is a function related to the parameter efficient fine tuning. And actually they support a lot of other fine tuning. For example, like the prefix tuning, P tuning, prom tuning, IA3, okay. But I do not explain all of them. So I just explain the important methods, for example, LoRa and QLoRa, because this is the most popular approach these days. Okay. So when you learn about the LoRa and QLoRa, I guess it is enough for the fine tuning. And if you can also apply in your final project, that it will be also good, because this LoRa and QLoRa is available with the GPT-2. Okay. And if you use some other kind of model, okay, yeah, you can check on the Hugging Face if they support with those models for free. Then you can just use it. If you need to pay some money for this model, then it means yeah, you can avoid those models. Okay, then those models, they also have the functions to do the fine tuning with those approaches. So it means if you have a new data set, then you can try with the fine tuning. Okay, I think due to the time, I will explain the Google Colab on our next class on Tuesday. Okay. So what we learned until now is about the fine tuning. We learn about the parameter efficient fine tuning. Okay. And for the Google Colab code, I think I will need sometimes to explain, because it will need very big parameters. Okay, because in some examples, I try to run the code for maybe 30 minutes. Okay, so I'm not sure if I can run during the class or not, but yeah, I will try to look at the details. If I cannot run during the class, then I will just show you the result, and then you can try to run at home. Okay. Okay, I think that's all for today's class. Is there any comment, questions?